I'm going to talk about property-based testing is a mindset, because it is. So this is my name on the internet. My real name is Andrea. I am a member of the Elixir core team. So how many of you know what Elixir is? Nice. So for those of you who don't know, it's a programming language, a functional programming language that is based on Erlang, which is another functional programming language, and it's pretty young. It's like five or 6 years old, but it's growing steady. I work at a company called Weedmaps. So how many of you know what Yelp is? Yeah. Yelp. Most people Yelp. Yeah. So Weedmaps is Yelp, but for weed. So you can go online and fetch information about like dispensaries that sell weed and doctors that prescribe weed, and this is all legal. It's an important disclaimer. Everything is legal because in the US, in many states, weed is legal for medical uses, and in some it's legal for recreational uses. So where it's illegal for recreational uses, it's way more fun, and we have more features. For example, we do deliveries, so you can order your weed online and get it delivered to your house, and you can also choose, which is really funny, the kind of drug deal option where the car stops at the corner of the street and doesn't come up to your building, so you don't, people that live with you don't know you're a pothead. That's really nice. So by now you should be sold, so weedmaps.com/careers if you want to work with us. So let's talk about testing. So why do we test? We test because if there's no test, we don't have really confidence in our code unless we try it out ourselves, but trying it out is very expensive. So we write tests so that we can cover a lot of cases and a lot of code automatically. So we can just run the tests and the software will check that everything works for us. So if there's no tests, we really have very low confidence in our code base. With tests, we are very less concerned with our code base because things are tested, and if the test pass, it means that they usually work. And also, we're really less concerned about breaking things that work because we have like a test suite that tests for regressions and makes sure that we don't break stuff. Probably the simplest type of test that we can do is unit tests. This is probably the most diffused technique. A unit test looks like something like this. I'm going to use Elixir in these examples, but this applies for most languages. So unit testing looks like this, where you have, for example, here we're testing a function that sorts list, and we're just testing that a bunch of cases. That we sort an empty list, it stays empty. If we sort a sorted list, it stays the same. If we sort an unsorted list, we sort it. This kind of testing, you can also call it example-based testing, because we're really testing that our code works for a few examples that we thought of. So in this case, it's the empty list, and a sorted list, and an unsorted list. You can also think of this kind of testing as table-based testing. So table-based testing meaning that you have a table of inputs and corresponding expected outputs, and you just test that the outputs correspond to their inputs when you run your code. So unit tests have some good sides because they're easy to write, they're easy to target. It's easy to target specific regressions, for example, specific corner cases. So it's easy to test the known corner cases through unit tests. The problem is that they're also hard to, they're not very good at, for example, expressing what the test is for. So in the previous example, it was like the function is called sort, so in this case it's quite straightforward. But it's like, from reading the test, it's not super straightforward what the function is supposed to do because we're not really expressive. And it's also hard with unit tests to find unknown corner cases because we're only testing examples that we come up with. So if there's unknown corner cases in our code, we're probably not testing them because we don't know about them. So enter properties. Property-based testing is a different way of writing tests. It's hard to write, so it's definitely more effort for writing property-based tests than is for unit tests. The way that property-based testing works on a high level is this. You basically take a bunch of valid inputs for your code. So you describe the shape of valid inputs instead of giving the tests a list of valid inputs. You just describe what the valid inputs are. And then you come up with a bunch of properties of the output. So you can say, okay, for any input, my output keeps these properties, right? So in the sorted list, it could be, for example, that the sorted list is still a list. So that's a property that for every valid input still holds. And then you give this stuff, the shape of the valid inputs and the properties that the output should always have, and you feed it to a testing framework. And testing frameworks are responsible for generating a bunch of inputs according to the shape of the inputs that you consider valid, and testing that running your code on those inputs actually holds the properties that you described. So basically you say, here's my valid inputs, generate a bunch of random inputs that are of this shape, and then test my code on these inputs and ensure that the properties are still being held. In these examples, as I said, I'm going to be using Elixir and Stream Data, which is a library that I wrote for property-based testing in Elixir, but this applies to any language that has property-based testing, which is most of them. So let's start with an example. We're going to just use the example that we used before for sorting a list. So let's come up with properties for sorting a list, right? The unit test that we had looked like this. So the first thing that we have to come up with is the value shape of the inputs. And the value shape of the inputs in this case is lists of integers. So for our function, we're going to consider that they can only sort lists of integers, but for lists of integers, all lists are valid. We can use empty lists, we can use negative integers, we can use lists with duplicates, so any list of integers is a valid input. And then we're going to come up with properties of the output that hold for any input that is a list of integers, or for any list of integers. The properties that we can come up with, for example, are that the output is a list, so the output will always be a list. The output should have the same elements of the input, so if I sort a list, I shouldn't take out elements or put in elements, right? And then the third property is that it's ordered. So in this case, we can just check that the list is ordered by checking that every number is either greater than or equal to the previous one, if it's sorted from smallest to biggest. So this is how a property-based test would look like, again, in Elixir, but this is kind of the idea for most languages. The first part on the top is the generator part, and this is where you describe the shape of the input, and then the property-based testing framework takes care of generating those random inputs. And in this case, list of integers in parens, that's what it says, that this is a list of integers, any list of integers. And then I'm binding that to the variable list on the left-hand side of the arrow. Then the next thing that we do in the block, so this is a code block, and in this code block what we do is we actually run the tests. So basically we assert the properties of our output, and the first thing that we do is actually run our code. So we have the sort function, and we call it on the list that we generated. And then we do a bunch of assertions on this. And in this case, as I said, the output is a list, it has the same elements, and it's ordered. Now, the same elements and ordered functions you can write pretty easily, so I'm not going to show, but the idea is that we assert the properties there. So if we were doing test-driven development, we would write a test and then start with a simple implementation just to make it pass, right? So you could start with an implementation like this. This would work. The problem is that it wouldn't pass the third property. So if you write the sort function which just returns the original list, it's still a list and it has the same elements, so it would pass 2 of the 3 properties, but it's not ordered if the list is unordered, right? So it wouldn't pass the third property. The nice thing is that, so say that it generates, the property-based testing framework generates a list like this, and with the implementation that just returns the list, so the bug implementation that we had here, this list doesn't really pass because it's not sorted. The nice thing is that, so this is a very random looking list, and it's very noisy. I mean, this is a simple example, so like it's not that noisy, but it's noisy. And the nice thing about the property-based testing framework is that when they generate data, they generate data at random, but when they generate data and find a failure, they try to shrink down the data to the simplest possible data that still fails the test. So in this case, the property-based testing framework will probably come up with something like this, saying the minimal reproducing example that still fails the implementation that you had is a list with 1 and 0. This is much easier to understand because it's basically saying it's any unordered list. And it's a small list, it's easy to understand. So this whole thing is called shrinking. And most probability-based testing frameworks have this, and it's really useful because probability-based testing is based on fuzziness, it's based on noise. So the data that gets generated is usually very noisy, and it's hard to understand why it's causing a failure. So it's nice that it can be shrunk down to a smaller version of that data that still causes the failure. So it's a really interesting tool. So generators, let me talk really quickly about this. So generators are just things that generate the data, so they're what we use for describing the shape of valid inputs. In Elixir, they're just basically streams of data, so you can just get any amount of random data out of them. They are composable, so for example, you can have, we have an integer generator and we have a float generator, and then they generate integers and floats respectively, and we have a one-off generator that combines multiple generators. So if I call one-off integer or float, it's going to return sometimes an integer, sometimes a float. So this is just the idea that generators are composable. You can do stuff like map functions over generators. So for example, if integer generates negative, 0, and positive integers, if we wanted a generator that only generates positive integers, we could just map the abs function, which returns the absolute value of the integer, over the generator, and it would work. So for example, if we want to write a ASCII string generator, you can just do it by having the integer generator, which generate code points, and then generating a list of those, and then mapping a function that converts that list of code points to a string. So this doesn't really matter how this works in Elixir, but the idea is that generators are composable in most property-based testing framework. So it's easy to write generators for your own custom data. Now, one thing that I want to talk about that is the single thing that gets asked the most when I talk about property-based testing is how do I write properties? How do I come up with good properties? That's the hardest thing about property-based testing, is coming up with good properties for your code. So this is a list of patterns that you can recognize and use to come up with properties, right? And the first one is circular code. Circular code is basically when you want to when you have a situation like this where you can encode something and then decode something, right? And the idea is that when you do this, if you encode and then decode, you get back with the original term. This is really easy to test with property-based testing because you can just generate random terms, then encode them, decode them, and ensure that nothing changed from the original term, right? So this is, for example, an example that is in the wild for an Elixir JSON library where you encode where you generate random strings and then encode them and then decode them again, and then you get the original string back. So the property-based testing framework is just gonna generate a bunch of strings and then encode them, decode them, and ensure that they stay the same. Another pattern that is really useful is the Oracle model. In the Oracle model, you have a piece of code that is your code and a piece of code that is called the Oracle in this case, and that's how your code should behave. So what you do, so for example, the Oracle code could be an older system that you're re-implementing, or it could be a less performant implementation that you want to make better or more performant. And the idea is that you test your code and the Oracle code on the same inputs and assert that the outputs are exactly the same. And the property-based testing framework again generates inputs at random, trying to find inputs that don't match. This is an example in the wild again where we have an Huffman encoding, which is some kind of encoding implementation in Erlang, and I was rewriting that in Elixir for a library, and I used this test to ensure that for every possible input, encoding it with my library gave the same result as encoding it with the Erlang library. Another pattern that I want to talk about is smoke tests. So this is really useful. Say you have an API that can return a bunch of status codes. So these are all the status code that it can return by contract, right? So what I can do is I can write a property-based test that checks that generates random requests to this API and performs those requests and checks that the status is one of those. So this is one checked for correctness. That's why it's a smoke test, because it won't check that the response is the right response for the request that you made, but it will check that the status is not an unknown status. So it's basically saying something nothing that is not expected is happening. Maybe the response is wrong for that request, but nothing unexpected is happening. And The last, I think, pattern that I have is to test most of your property-based tests, to put most of your property-based tests effort in CI, in continuous integration, because the idea is that property-based tests are slower than unit tests because they have to generate a bunch of inputs. And usually, for example, in the Elixir library, we generate 100 inputs for every property-based test. And the idea is that if you generate 100 inputs, it's like if you're doing 100 unit tests for each property-based test that you have. So the idea is that if you do most of that in CI, then it's much better because CI can run as long as you want, and you have a much quicker feedback loop. So, for example, in Elixir, it could look something like this, where you configure the maximum runs to be 500 in CI, so meaning that the property-based testing framework generates 500 inputs in CI and only 25 locally. Again, locally, you're just testing all the time, so you're still trying a bunch of different inputs, but CI is doing the heavy work. And no, the last one that I have, this is really important, that I get asked is, how do I test, for example, corner cases with properties? How do I ensure that my generator generates some specific data that I want to test? And the answer is, you don't. So your generator generates random data, then you can also use unit tests together with property-based tests, so they're not exclusive. So the idea is that if you have, for example, a property-based test for checking some function, then you can also, and that checks the general, it checks the properties of that function for any generated input, but you want to be sure that for specific inputs it works as you say, then you can add the unit test that tests for that. And this is also useful for example, in this case, I'm not going to go through the example, but in this case, the property-based test is actually testing properties that do not test the correctness you never actually test that the function is doing what you want. You only test that the property that you want of the code. So in this case, it's concatenating string and asserting that the concatenated string starts with the left string and ends with the right string. So you're testing that this is true for all strings, but you're not testing where this actually happens. So if you have a unit test for that, it's perfectly fine having a unit test. One thing that I will not go through, but I want to mention, is stateful testing. So stateful testing is about having, so everything we talked about right now, until now, is stateless property-based testing, which means that we basically just generate data and test it against our code, but we don't really test the behavior of our code over multiple calls, if we can call them calls. So basically, we don't test the behavior of our stateful pieces of code. And property-based testing kind of solves that as well. So we don't have this yet in our Elixir library, but there's ways to test stateful systems. And the basic idea, I'm going to go over this very quickly. The basic idea is that you have a model that represents the system that you're testing, and then you have a bunch of commands that you can run on that system, and then you assert that commands do something both to the model and then to the real system. So for example, you could be modeling Redis with a symbol dictionary, key value dictionary, and the model will be the dictionary, and you would have operations that set and get a key on both Redis and the dictionary. And you would check that if you do an operation on Redis, then you can see the result of that operation in the dictionary as well, and it corresponds to the result that you have in Redis. So again, setting a key or getting a key. So I'm not going to go over all this stuff because we don't really have time. One thing that I want to mention is that property-based testing is actually useful. It's not just a theoretical thing. So I know of this example in level 2B where they used property-based testing and found a sequence of 17 calls to the database with stateful testing that caused a bug. This is really hard to find, and this is the minimal reproducing case. So like this was the smallest possible thing that they could find that broke the database, and it was 17 calls. So it would have been really hard to find for a human. And then they fixed this bug and ran it again, and they found a sequence of 33 calls that broke the database. This is the minimal case, so a human would have probably taken way more calls, and like it would have been really hard to find the smallest possible set of calls that would break. So this is actually useful for the real world. So then we are doing some research for, I'm not going to go really over this, but we're doing research on how to integrate this with type annotations in Elixir. So Elixir is not typed, but we have annotations that are just there mostly for documentation and for a tool called Dialyzer, and we are working on generating, having generators that run from types so that you can do something like from type and give it type and have a generator back. And then we can do, since we have specs that tell you what a function takes and what it returns, we want to turn those into property-based tests so that you can actually just write the spec, for annotate the types of the function, and have the property-based test, kind of do a smoke test as well of that function. Most of this stuff was, so for the library I have to thank ClojureSpec. So this was the library that kind of I copied all of stream data from. And the conclusion, so this is the stuff that I mostly use for property-based testing. This is all good reads. So Erlang QuickCheck is the probably most famous property-based testing libraries for Erlang. QuickCheck, automated testing of Haskell programs, is the original paper that introduced property-based testing for Haskell. A really nice website is propertesting.com, which is for Erlang, but it's definitely interesting for other languages as well. So to recap, property-based testing is good to find obscure bugs, to reduce failing inputs to a minimal and easy to understand input, sorry. It's useful to find specification errors, because sometimes like writing property-based tests helps you also validate how you design your code and how you think, so what inputs, for example, you think your code takes. So that is really good, and it's good at covering a vast input space because it generates inputs at random. So use property-based testing, whatever language you're on, because most of them have it. I know that these have it for sure. Probably a lot of the languages have it as well, so you can use it whatever language you're in. So that was all. That's my name on the internet, and that's, if you're interested in the Elixir library, that's the link. Otherwise, that's all.
We have time for one question. Who wants to ask it? Right here.
Hi. Can you tell us a little bit more about the facilities for actually shrinking the test case to the most minimal possible input? Yeah. How does that work? Like, especially if you have your own custom generator for your custom data. Yeah. Thanks.
So to do that, we made the choice of only letting you write generators by combining other generators. And you can, so as far as we know, you can generate anything still. But the idea is that when you have a generator that is built in, like integer, it knows how to shrink. And when you have combinators like one-off, they also know how to shrink. So you can use basic generators that know how to shrink, combine them however you want, and they will still know how to shrink. And that means that your custom generators will know how to shrink as well. The way that it shrinks is a bit more complex, but it's basically we generate a lazy tree of possible shrinks, and we don't realize that tree until we need it for shrinking. And then when we need it, we start going down that tree and creating smaller inputs. And that's the way we do it. Yeah.